Hello everyone. Today again we are going to discuss with the continue part of the chapter wave optics in this session 8. So in this session we will discuss regarding the diffraction of light. So already in the previous lecture we know regarding what is the interference of light. In this it is a diffraction of light. So diffraction means it is the phenomena of bending of light waves around the edges of the obstacle, and afterwards it will entering into the geometrical shadow of the obstacle, and it is called as the diffraction of the light. So whenever the obstacle is there, so at that time what happens, the light waves that will be bent towards the edges of the obstacle, and afterwards they will enter into the shadow area. So that will be understood with the help of the diagram. So in this diagram the slits are there. The slit is nothing but here the obstacle. So with the help of an obstacle, what happens, that will be light is bended towards the edges and it will be entered into that shadow area. It has not bent towards it is, but it has entered into the shadow area. Similarly, one more diagram you can observe. So because of the obstacle it has bent towards the edges and afterwards it will enter towards the geometrical shadow of the obstacle. So this phenomena we can call it as it is a diffraction of light. So again there are two types of diffraction that we are going to discuss now. There, one we can call it as it is a Fresnel diffraction and another one is Fraunhofer diffraction. So in Fresnel diffraction what happens, the spherical or cylindrical wavefronts which are used to get the Fresnel diffraction, but in Fraunhofer the plane wavefronts which are used to get that Fraunhofer diffraction. And similarly in Fresnel diffraction, the source, obstacle as well as the diffraction pattern, that is nothing but the screen, which are at the finite distance. But in Fraunhofer diffraction, the source, obstacle as well as the diffraction pattern, means the image screen, which are at infinite distance. Similarly, the third one is the optical device is not used in obtain the diffraction. In Fresnel diffraction there is no optical device are used, but in Fraunhofer diffraction the convex lens which is used to obtain the diffraction. Similarly, the Fresnel diffraction, which is very difficult to study as well as it is obtained in the laboratory, but in Fraunhofer diffraction it can be obtained as well as studied in the laboratory itself. So next we will discuss regarding what is the diffraction of a light at a single slit. So for this I will consider one diverging light from a monochromatic source S. So in diagram you are observing the S, that is one the monochromatic source, but it is one diverging light. Now this diverging light which is made parallel after which is refracting to the convex lens L1. So once it will enter into the convex lens, all these diverging beams becomes converges. Then the refracted light from the L1 which will be propagate in the form of plane wavefront. So now it will become plane. So it will become plane wavefront now. That L1 is propagated in the form of plane wavefront, that is the plane wavefront we can write it as it is W dash. Then the plane wavefront W dash is incident on the slit AB of a width d, or which is at a distance d. So according to Huygens principle, each point of the slit AB which acts as a source for the secondary wavelets. Next, the convex lens L2 which helps in converging the parallel beam. Now we have to consider the point O on the screen which is at a distance capital D from the slit AB. Since point O which is equidistant from point A and B, so the path difference between them is 0 and the constructive interference will takes place here, and we are getting the central bright fringe at a O, and it is called as the central maximum. Now let the diffracted light through an angle theta Then so the secondary wavelets are also diffracted through an angle theta. So suppose once that light will be diffracted through certain angle theta, then our all the secondary wavelets, they will also diffract through certain angle theta itself. Let these wavelets, they will meet at a point P on the screen. So just to observe in the diagram, they will meet at a point P on the screen. Then whether this point P is having maximum intensity or minimum intensity, that will be depend upon the path difference. So because of course here the path covered by them is not same, because O is at equidistance from them, therefore the path difference is 0, therefore the constructive interference will be taken place here and we are getting the maximum brightness. But in this case point P, the path difference is there. So because of path difference, what is our maximum intensity or minimum intensity? So that you have to get with the help of the path difference itself. Then so the path difference between the secondary wavelets which are reaching the point P from the corresponding wavefront. So now we have to calculate what is our path difference now. So again the same diagram we have considered. So the path difference, to find the path difference between the secondary wavelets which are originating corresponding points A and B of the plane wavefront, then for that we have to draw perpendicular, that is AN perpendicular to PB dash, means B line which is propagating towards the point P. So that BB dash we have taken one perpendicular, that is AN we have taken the perpendicular. Then the path difference between these waves or these wavelets which are originating from A and B is nothing but Bn. So Bn is our path difference here. Bn is the path difference. Therefore from the triangle ANB, just in diagram you observe the triangle ANB, that Bn divided by AB, that will gives you sin theta. Bn divided by, because it is an opposite side, divided by hypotenuse, that will gives you the sin theta. Or Bn, what is our path difference? That Bn is equal to, it is AB sin theta. Or we can write this, Bn is equal to, AB is nothing but the distance d sin theta. If theta is very small, then our sin theta is approximately equal to theta itself. Therefore Bn is equal to d theta. So this Bn, whatever the path difference is there, that Bn is equal to, it is d theta we are getting. Suppose if you imagine, if the path difference is equal to lambda, means that Bn is equal to, if you consider it as a lambda, then our point P will be at a maximum intensity. The point P will be at minimum intensity. How it will be minimum intensity, that we can observe here. So it is called as, that is a minimum intensity, therefore it is called as first secondary minimum on either side of the central maximum. So in this case what happens, our whole wavefront AB, that will be divided into two equal halves, that is one is AC and another one is CB. That is two equal half part it will be taken place, one is AC and another one is CB. So now if the path difference between the secondary waves from A and B is equal to lambda, then the path difference between the secondary from A and C reaching the point P will be lambda by 2. So just to imagine here, whole AB is equal to what? It is a lambda. So that AB itself we are divided into the two parts, one is AC and another one is CB. So that lambda is also divided into the two parts. So AC is equal to lambda by 2. Similarly CB is also equal to lambda by 2. Also for every point in the upper half of AC of the wavefront, there will be corresponding point in the lower half of CB, for which the path difference between the secondary wave reaching the point P is lambda by 2. So therefore both are lambda by 2, the pairing will be taken place, that will be cancelled. Thus the destructive interference will taken place here at a point O, and it is called as the first secondary minimum here. It is called as the first secondary minimum. Therefore we can write the angle of diffraction, that theta, for which the first secondary minimum that will be produced by, that is d sin theta is equal to lambda, because we have considered the path difference as lambda. Therefore our d sin theta is equal to lambda, or sin theta is equal to, it is lambda by d. For theta is very small, then our sin theta is approximately equal to theta. Therefore theta is equal to lambda by d. We are getting it as for if you consider the path difference as lambda. Next we will consider the same thing again if the path difference between the secondary waves from A and B is equal to 2 lambda. Suppose I have taken only the slit and the distance now. It is, if you consider it is a 2 lambda, then the point P, which is the position of the secondary minimum. First we have considered it is a lambda, that is our first primary minimum or the first minimum, and the next one is, if you consider it is a 2 lambda, it is second secondary minimum we are getting. How we are getting it as a minimum itself? Now what happens in this case, the whole wavefront AB that will be divided into the 4 equal parts. So in this case what happens, the whole wavefront AB that will be divided into 4 equal parts. So the path difference between the secondary waves from any 2 corresponding points is equal to lambda by 2. So it is entirely, it is 2 lambda, means 4 equal parts if you are doing, means 1 is lambda by 2, all these 4 values are lambda by 2 itself. Then they will reach the point P. Hence they interfere destructively and produce the minimum intensity. How they interfere destructively means lambda by 2 and lambda by 2. First 2 they will get the pairing, so both the values are cancel each other. Similarly last 2, again lambda by 2, they will also cancel each other. Therefore you are getting it as a 0, that is minimum intensity that will be produced in this case. Therefore in general the angle of diffraction theta n for the nth secondary minimum, that is given by d sin theta n is equal to n lambda, where n is equal to 1, 2, 3, 4 and so on. Therefore if you are getting n, if you are substituted as 1, means it is lambda. For lambda also we got it as it is a minimum intensity. N, if n equal to 2 you have substituted, it is 2 lambda, 3 lambda, 4 lambda, so on. So all these values we are getting it as a minimum intensity of a point for a point P. So this is for minimum intensity. Next, one more point if you have considered, that is if the path difference between the secondary waves from A and B, suppose if it is equal to 3 lambda by 2 or 3 by 2 lambda, then the point P dash, generally point P we have taken in the diagram, or another one point, that is P dash, that is the position for the first secondary maximum. How it is maximum in this case we will study. So in this case what happens, the whole wavefront AB that will be divided into 3 equal parts. So the path difference between the secondary waves is equal to lambda by 2. In diagram you observe it is 3 lambda by 2, means our whole wavefront will be divided into the 3 parts. So that is lambda by 2 and lambda by 2. So first lambda by 2 it will be cancelled with the second one, that is pairing will be taken place. So only 1 lambda by 2 is left out, that is given here. What is that? In this case the wavefront can be divided into the 3 equal parts. So the path difference between the secondary waves is equal to lambda by 2. But here we get one pair of lambda by 2 that will be cancelled and 1 lambda by 2 is left out. That leads to the bright intensity or the maximum intensity, and it will interfere constructively. So in general, the angle of diffraction for which the secondary maximum is given by d sin theta n is equal to, it is 2n plus 1 lambda by 2, where n equal to 1, 2, 3, so on. Suppose if you have substituted n is equal to 1, it is 3 lambda by 2, n equal to 2 is 5 lambda by 2, n equal to 3 is 7 lambda by 2. For these all values, we are getting it as maximum intensity. And similarly, next, the intensity of the secondary maximum is small and it is rapidly decreases as we go for the higher values of n. So intensity for the secondary maximum is small. However, first one is the middle bright is there, that is the central maximum. Next, afterwards what happens, the intensity goes on decreases, and afterwards it will be rapidly decreases for higher values of n if you have considered. So if theta is the angle of diffraction for the first secondary minimum, then the angular width of the central maximum, that will be given by 2 theta is equal to 2 lambda divided by d. So if theta is what? It is the angle of diffraction for the first secondary minimum, then the angular width of the central maximum. The central maximum width means it is the width of the two maximas, the center of the two maximums you have to consider, that will be given by 2 theta is equal to 2 lambda divided by d. The linear width of the central maximum, it is the distance between. So now we have considered the linear width. So the linear width of the central maximum, it is the distance between the first secondary minimum on either side of the central maximum at O to the first secondary minimum at P. When the screen is at a distance d from the slit, then our sin theta is approximately equal to theta, that is equal to, we can write it as it is, x divided by capital T, that equal to lambda by d, or generally we can write x is equal to lambda d by d. Therefore, the linear width of the central maximum. So first one width we have got it as it is x is equal to lambda d by d. But the linear width of central maximum, it is for only half of the portion. X means it is only half of the portion, but 2x, but that is full entire width of the central maximum, that is given by 2x is equal to 2 lambda d by d. So as a slit width increases, the width of the central maximum decreases. For large values of slit width, the diffraction pattern is not observable. So now this will be understood with the help of graph, that is the diffraction pattern which is obtained on the screen consists of central bright band followed by alternate dark and bright bands of decreasing intensity on either side. The intensity variation on the screen is represented graphically. So this is our graph. So middle one, that point O, that is I, that is intensity. The middle one is what is the central maximum, that is central bright band. So whatever the x we have considered, that x is nothing but it is a distance, only the half of that. So lambda by minus lambda by 2 to O, or O to lambda by 2, whatever you have taken, that is called as x. Therefore 2x means it is entire width of our central maximum. So this will be given by graphically. Next, we will discuss regarding what is the difference between interference and diffraction. So interference as well as the diffraction. In the first point, interference is the modification in the distribution of light energy or the light intensity due to the superposition of two light waves. So it is what? The distribution of light energy or the light intensity because of the superposition. But the diffraction, it is a bending of light around the edges of the obstacle and spreading into the geometrical shadow of the obstacle. Spreading, or you are entering into the geometrical shadow of the obstacle. Next, the second one is interference is due to the superposition of two wavefronts which are originating from the coherent source. Already I told in the previous lecture itself, to get the interference pattern, the source must be the coherent source. But in diffraction, that is diffraction is due to the superposition of the secondary wavelets which are originating from the different points of the same wavefront. here it not must be the coherent source. So from different points you are getting from the same wavefront. Next difference we will discuss, that is interference pattern consists of alternately bright and dark bands, at all the bright bands being the same brightness. So in interference also we got one bright as well as the dark bands, but all these bright as well as dark bands which are having the same brightness means same intensity. Here the intensity does not going to change. But in diffraction pattern, that is, a diffraction pattern consists of central bright band which is the maximum brightness, followed on either side by alternately dark and less bright bands. They are called as secondary maximum. As the order of secondary maximum increases, its brightness decreases. So middle one, that is the central bright, whatever we are having, which is having the maximum intensity or the maximum brightness. After this, whatever the secondary maxima minima we are getting, the brightness of this bands will be goes on decreases. Here all these bright bands, they are not at all in the same intensity, but in interference all these bright bands which are at the same intensity. Next is, in interference pattern the width of the fringes, that is bright and dark fringes, is equal. That is, already we have calculated beta is equal to lambda d by d. That value, the width of the bright fringe as well as the dark fringe, which is equal in this case, that is in interference. But in diffraction pattern, the width of the central fringe is double than the width of the other maximum. Therefore we have taken the width of the central maximum is 2x, we have written, just to observe in the notes, that is 2x, because the central maxima is very much the larger, that is central brightness, but in other cases the width of the other maxima goes on decreases. Next is the last point in case of interference. In interference, bands are equally spaced, that is good contrast between dark and the bright bands which exist. So you can easily differentiate which one is the bright and the dark band. That is clearly shown in case of the interference bands. But in diffraction, bands are unequally spaced, means that is the contrast between less bright and the dark bands is comparatively lesser. Here the contrast is not at all good. In this case what happens, the bright band which will be mixed up with a dark and dark will be mixed up with a bright. So clearly where it will be ends, that we are not getting clear picture. But in diffraction pattern, clearly we can say at a distance from this beta is equal to whatever we have calculated, at that distance this is the bright band, this is the dark band, we can clarify or we can separate them. This is what the difference between the interference and the diffraction. Just go through this.